Let's talk about GPU benchmarking model workloads. When choosing where to deploy a given model, it can be challenging to determine what you actually need. As a starting point, you can look at the size of the model and figure out which setup has the amount of RAM that you need, but that's just going to tell you the minimum setup that can run your model. The real question is, what are you going to be using that model for? And that's going to drive what you're going to measure, because results can be measured in a whole bunch of different ways. For our benchmarks, we measure 5 areas: batch size, token count, throughput, average latency, and wall clock time. Batch size is the number of concurrent requests sent to the server. This is dictated by you as the person running the benchmark. Batch size is one of the most important knobs in LLM benchmarking because it directly controls how much parallel work you're asking the system to handle at once. Running benchmarks across multiple batch sizes gives you insight into both latency behavior and throughput scaling, which you can't see from a single batch alone. The batch size you choose depends on how you anticipate your usage to grow. For example, a batch size of 1 measures latency, as in how fast a single request runs end to end. Larger batch sizes test throughput, showing how well the endpoint scales when handling multiple requests at once. If throughput grows but average latency also grows significantly, that can signal saturation of GPU or system resources. Token counts are the number of input tokens, output tokens, and total tokens actually processed by the model. Input tokens are all tokens the model must read before it can generate a response. This includes your system prompt, the user prompt, which is generally some synthetic text, any formatting or messaging structure added by the API you're using for testing, like the OpenAI Chat Completions API, for example. This is why, when you benchmark, you'll have a target number of input tokens, but the observed input tokens will be higher, so don't be shocked when your input tokens don't match what you configured. Output tokens are the tokens generated by the model in response to your prompt. In our benchmarks, we explicitly cap our output tokens, so output tokens are typically close to the configured value. Minor deviations in the number of output tokens can still occur due to early stopping, end of sequence tokens, and safety or truncation behavior. Output tokens are usually more predictable than input tokens, so this number will more closely match what you configured. Total tokens processed is the sum of input and output tokens. This number best represents the actual GPU work performed, compute cost, memory pressure, and attention complexity. Even though throughput is often reported as output tokens per second, the GPU is doing work on both input and output tokens. Throughput is the number of tokens processed per second, often broken down into input tokens, output tokens, and combined tokens. We often simplify benchmarking to a conversation just about tokens per second, as it's easy to understand that the more tokens that can be processed per second, the faster you'll get back a response from your model. Our benchmarks measure output tokens over wall clock time. Average latency is the average time required to compute a single request from submission to completion. We measure average latency as wall clock time over successful requests, as reported in seconds per request. Wall clock time is the total elapsed time from when the batch of concurrent requests is launched to when the last one finishes. It reflects end-to-end system behavior, model execution, batching inside the LLM, GPU scheduling, memory pressure, queuing, and any networking overhead. Wall clock time helps you expose scaling issues. When you increase batch size, you expect throughput to increase or at least plateau, and wall clock time to grow sublinearly or at least stay roughly flat compared to your batch size. If instead you see your wall clock time growing linearly or super linearly with your batch size, or you see sudden jumps in wall clock time between 2 batch sizes, that usually means that you've found a scaling bottleneck, such as GPU saturation, KV cache or memory pressure, internal request queuing inside VLLM, or CPU or networking contention. Wall clock time is more useful than measuring average latency alone because average latency can hide problems. For example, if half your requests are fast and half are very slow, the average may still look acceptable. Wall clock time captures the slowest path in the batch, which is often where scaling breaks down first. So, We have these 5 measurements. We run the benchmarks on different GPUs at different batch sizes, and we get back some results. Which numbers should you care about most? How do you choose from the trade-offs? For interactive real-time applications like chatbots, copilots, or UI-driven tools, average latency matters most. For example, how fast can you start getting a response back to the user so they don't feel the wait time? Choose a GPU that can perform well on 1 to 4 batch size requests, as smaller batches will give you lower latency. For multi-user APIs or production inference servers like SaaS APIs, internal services, and developer platforms, focus on how many users you can serve without slowing down. Throughput scaling with batch size, and wall clock time trends tend to be most important to focus on. Choose a GPU that supports efficient batching so it will handle more users per dollar. For offline or batch generation workloads like data generation, evaluation runs, and embeddings, users aren't waiting on a response, so latency isn't that important. Instead, focus on how fast you can get the job done. Peak throughput and wall clock time matter most, along with memory capacity to support the large batch sizes you'll need. For these types of workloads, choose the GPU with the highest sustained throughput at large batch sizes. So as you can see, the type of GPU you need depends on what you're planning on doing with your model. Two developers can look at the same model benchmarks and end up deciding on different GPUs based on how they're going to be using that model. There's actually so much more I could say about benchmarking, so if you find this useful, let me know and I'll go into how I ran our benchmarks and what information I found.